Okay, so let's look at the same exact problem. I even left the work from the previous problem up, but let's take the same problem and say, okay, well, let's say there's friction. Let's say that there's a mu of zero point 0.2 between the objects. Now, look, I can do the same thing. I can combine the objects as one overall situation, and we're going to assume for these problems that that mu is the same mu between each of the same objects on the same surface. We're not going to assume there's two different kinds of boxes with two different kinds of surfaces and giving us two different kinds of mu's. That would create some difficulty. So we're going to keep it simple, at least in that way. And if that's the case, those frictions, if it's the same mu's, they're just going to have each box is going to have a friction, but those frictions as a system are going to add. We're going to get a total friction there. And so we can do that if we combine the system. And this is a force friction kinetic. And if that's the case, we can still use, this base equation, summation of forces in the x equals ma. We just have to, tweak the summation of the forces aspect. So we know there's a force. Now we just have to, add in subtract the friction. Now, of course, we know that friction can be thought of as the mu k times the normal force. And this would be the normal force of A and B. So we do now need the y direction analysis, right? We need to find that normal force. So, force, actually I should, before I do that. So summation, that's terrible. Summation of the forces in the y equals 0. Force normal A, B minus F, G, A, B equals 0. Force normal A, B equals MA plus MB times G. Let's get a little crowded in over here. So let me see if I can move some of this stuff out of the way. We're just going to erase this because we're going to come up with a different answer anyway. And let's see if we can scoot this down just a little bit so I can give myself some room. And if you go and solve this, it's equal to 3.0, right, times 9.81. And that, I don't have that ready. Why do I not have that ready? It's 29.43. Right, so now we know that's 29.43 for the overall normal force. That's all of the mass. So we can substitute that in. 10.0 minus the 0.20, 29.43 is the normal force, equals 3.0 times A. That force of friction is 5.9-ish, 5.89 actually, or if you round. All right, equals 3.0 A. Sorry, it's a little squished. And the acceleration, if you solve this, is 1.37. A little rounded, but 1.37 meters per second squared. And so that's my acceleration overall of my system forward. Okay, great. But how do I find the tension? Well, same thing. We can find the tension. And let's do the following. Let's take all of this. Am I going to squeak it in? Nope, nope, nope. Let's see if we do this again. Okay. So let's take our free body diagrams that we had before. And now we have to add the friction to each one, right? So, you know, each box is going to have that friction. And it's not combined anymore. So, yeah, we can have two forces acting in the same direction. That would be box A's kinetic friction. And this would be box B's kinetic friction. That can happen. And that tension is still connecting the boxes. So now we have to do our analysis. And we already now know, too, that, you know, the analysis in the y direction is going to be important because we're going to need those normal forces. Not that it's very difficult because, you know, everything is horizontal or vertical. So finding those normal forces is easy, right? Because the normal force is basically going to be equal to the gravity. But still, that's going to change a lot of the work that we had done before. So I'm going to keep the same statements, except I have to add or subtract the friction in now, in each case. So let's do that. Now I guess I should just rewrite these things. I don't know why I'm messing with this way, but I'm just trying to show that, you know, minus force friction kinetic B. And this would be minus, and I guess I've got to move this over a little bit, minus force friction kinetic A. So we got another force to deal with. And, you know, I'm trying to find that tension. And that's going to be equal to mu k, same mu k, force normal B equals MBA. Now, what some books do, and if we just realize conceptually that the normal force and gravitation are going to be equal to each other, equal but opposite to each other, because of the because there's nothing at an angle adjusted to normal force, some people will just literally plug in here the gravitation for the normal force. Now, that's a practice that you have to be careful about, because if you do that all willy-nilly when there's angles involved, you're going to get things wrong. So, but I'm going to do that here. And then I can even, you know, plug in numbers. We can do the following. Now, again, we're going to pretend that we didn't know. No, I'm sorry. So we can plug in numbers. So, but I'm gonna stop here for a second because we can solve this now. You know, if we know the acceleration of the system, we can solve this here. I'm going to do the same thing for A. You know, same thing. Same concept as before, except we got now an extra force to deal with. And yeah, I'm just going to take this home with the appropriate substitutions. And again, because there's no angles involved, the normal force isn't changing, so the normal force is going to be equal to the weight of A in these simpler problems. And so, you know, since we know the acceleration, we know the mass, we know the g, we know the mass, we know the mu, I can solve for ft. And same thing over here. I know the acceleration because I solved it for the entire system. I know the mass, I know the g, I know the mass, I know the mu, I know f, so I can solve for ft. So I can solve for that if I want to. And if you go and solve for the tension, you're going to find that the tension is the same exact as it was in the previous problem. You're going to find the tension is going to be 6.67. Why is that? Well, look, the acceleration is less, but this force is still got to pull these objects in, with the same motion. And so because that friction is identical, or not identical, but because that friction is proportional to the weight, and the weights have the same ratio, the ratio of the frictions are going to be the same to pull it forward, and that tension is going to remain the same between it. Now, that doesn't always happen with other problems in other directions, so don't always think that that happens where you think the tension is going to be the same with or without the friction. But in this case, it does work out, and you can prove that to yourself. But what I wanted to also point out is that if you didn't solve for the overall acceleration of 1.37, you could also have solved this with the substitution method 2. And so what I'm going to do is I'm going to push this up here. I mean, this will work either way you do it. So let me plug it in. Oh, I keep forgetting MB is 2.0. And I think if it's not exactly 6.67, oopsie, if it's not exactly 6.67, it gets pretty close because of the rounding. And then the same thing over here. Because again, you know all this information because we solved for the system as a whole. There's a little error here, so let me fix it real fast. I need to take this over, put this over here. This should have had G, so we need 9.81, and then now it should work out.